a circle, all the points on a circle have something in common. Every point on the circle is the same distance from a single point, which is called the center. Sometimes we use the word locus to say that this is the circle is the locus of points, a fixed distance from a given point. The center. Locus means just like this. Locus is like a fancy word for the set of points that have this location or this property. Well, there's also a locus definition of a parabola. And the way it works is this. You have a line. The line can be vertical, horizontal, any direction. We call that line the directrix. And we have a point anywhere you want, and that's called the focus. And there's a property. Now, any point that you could name, like this one, this point is, if I measure the distance to the focus and then measure the distance to the directrix, this perpendicular, they would not be the same length. On the other hand, maybe there is a point, somewhere over here, let's say, where this distance and this distance were somehow the same. Well, for any focus and directrix, if you take the collection of all the points that are the same distance from the focus as from the directrix, like this one, or maybe some point kind of over here, I measured this distance and this distance. These two distances would look equal. Anyway, if I made them all, they would make a parabola. And what's called the locus definition of the parabola is that every point on it is the set of points that for each point, if you were to measure the distance to the focus and the directrix, those would be equal to each other. Although these are not necessarily the same, and they actually have to be different than these. But the yellows would be equal to each other, and the blues would be equal to each other. Well, this leads us to an activity then. If you take a piece of paper, piece of loose leaf paper, and you put a point somewhere on it, and here are the lines on the loose leaf paper. If you take some point at the intersection of one of the lines, the vertical lines, and if you were to make a fold, folding the red point onto this black point, you get a fold like that. And then, if I make a point where the fold intersects the vertical line, that point is equidistant. It's the same distance from the focus and the directrix. And that's, well, the simplest reason is that it's a perpendicular bisector, and there's a theorem that any point on the perpendicular bisector of this segment here is equidistant from the two endpoints. But it's also true, if you want, because of similar triangles. Of course, these two line segments would have to be equal because of sort of the fold made that happen, and this line segment here is sort of reflexive, and that would make these two by corresponding parts of congruent triangles. So if I pick another point on another one of these lines, and I make this folding the red point onto the black point, and then I find the intersection here, that will be yet another point that's equidistant from the focus and the directrix. And if I keep doing that, I will get this parabola shape. Depending on where you put that focus point, you might get a different looking parabola. Like if I pick it really close to it, I'll end up with sort of a skinny parabola. One thing to notice is that the vertex is halfway between the focus and the directrix, and that is going to come in handy later. So once you know this idea that for any line and point there's a parabola, that's the collection of points that are equidistant from the given point and the given line, we can take this kind of strange graph paper. It's got horizontal lines and it's got concentric circles. And for the first question, they want you to notice that points A and B, if you just count concentric circles, they all have, each radius is one more than the one before. So I can count here 1, 2, 3, 4. It's 4 units away. A is 4 units away from B. Now from B to line 1, which is the perpendicular distance, because of these parallel lines that are all 1 unit apart, we can see 1, 2, 3, it's 4 away. So if I'm looking at line 1, so I'll make red, and point A, then this point here would be a point on the parabola because it is, that point is 4 units away from A and 4 units away from line 1. I want more points on that same parabola, and this graph paper allows me to do that. This point is on that same circle, so it's 4 units away from A, but it's also on the line that's 4 lines above line 1. So those are 2 points. But what about points that are 3 away from A and 3 away from line 1? Well, 3 away from A is going to be on this circle number 3, but 3 away from line 1 is on this third line above the red line. So that makes this point and this point. But there's also points that are 2 away from A and 2 away from 1. Those are on the second circle and the second line. And there's even a point that's 1 away from A and 1 away, which is over there. And I could sort of see, it's sort of like it's like a little, I can actually make other points here. 5 away, 6 away, 7 away, 8 away, 9 away. And when I connect them, it makes a nice parabola. Now if we keep and the point A is the focus, the center of this smallest circle. Now if instead I want to use a different line as my directrix, let's say instead of using this line, I use this line here, which is closer to the focus, and I'll use a different color for my parabola. Now, points that are 1 away from A and 1 away from line 2 are actually on this small circle, but on the first line above it. So it's these 2 points. And when I do this for 2 away from A and 3 away from A and 3 away from the line and 4 and 5 and 6 and 7, I get these points. So it's sort of a thinner, skinnier parabola there. Now I don't quite see the vertex of that, because that vertex is half away from A and half away from line number 2, so I'll make a point sort of in the middle there. So these 2 parabolas have the same focus, but they have different directrixes. The green one, directrix, was at, if I call this focus 0, 0, the green parabola's directrix is at y equals -2, and for the blue parabola, the directrix is y equals -1. Okay, so that shows you what I've gone over is how we could use paper folding to create points on a parabola, and how we can use this concentric circle and horizontal line graph paper to also create different parabolas. If the directrix is above the focus, like if I want to use line number 4 as my directrix, now the points are going to be, it's going to become basically an upside down parabola. something like that. So the focus can be below, and you could even have diagonal directrices and things like that, but for now they're just horizontal lines.